Okay, so after that discussion of problems that don't work out and where you can't apply the fundamental theorem, let's look at some more problems where you can. So this example tells us to evaluate the following definite integrals. This is often how problems will be phrased. A lot of the exercises are worded like this. So for part A, we're going to take the definite integral from 0 to 2 of x squared plus 1 with respect to x. Part B, we're going to take the definite integral from 0 to pi over 2 of cosine of x. And then for part C, we're going to take the definite integral from negative pi over 4 to positive pi over 4 of the function. Our integrand this time will be secant squared of x. And then part D, can I fit one more on here? I'll put it right here. I think we can fit part D on here. So part D is going to be the definite integral from 0 to 4 of the square root of x plus x squared. Okay, so I got those all on that page, which is nice because now we can slide it up like that, and I can pull this page down and we can carry on. Okay, so let's solve these. And if you want, maybe even don't hesitate if you're feeling ambitious and you want to give these a try, just pause the video and try them on your own first. And then watch how it's demonstrated here afterwards and compare. But now let's work through these. So for part A, well, we've got the definite integral from 0 to 2 of x squared plus 1. Well, we need an antiderivative for x squared plus 1. Well, for the x squared part, we can use the power rule, and we'll get x cubed over 3. Right? You can check in reverse that if you differentiate x cubed over 3, you're going to end up getting x squared. And then for an antiderivative for 1, we can just write x. So remember, two functions that are added together, if you want to take the antiderivative of the result, it is totally fine to just take the antiderivative of each one separately. That works for addition and subtraction, but that does not work for multiplication and division. So be very, very careful you don't accidentally make that mistake. Okay, and we'll get a chance to, in 5.4, we'll see some situations where we encounter that problem. But for now, this you can check in by differentiating that this is actually an antiderivative of x squared plus 1. So let's copy our bounds, 0 to 2, and then plug them in. Okay, so you get 2 cubed over 3 plus 2 when you plug in x equals 2, and then you plug in 0, and you're going to get 0 cubed over 3 plus 0. And then that just works out to 8 over 3 plus 2, which if you get a common denominator, that'll be 14 over 3, because 2 is actually 6 over 3. So you can just add 6 and 8 to get 14. So for part B now, we've got the definite integral from 0 to pi over 2 of cosine of x. All right, so we need an antiderivative for cosine again. We've actually seen this one a few minutes ago. A good antiderivative for cosine is sine. So we can go sine of x from pi over 2 to 0, and then just plug them in. So you end up getting sine of pi over 2 minus sine of 0. So this is actually equal to 1, and sine of 0 is equal to 0, so you end up getting 1 for the result there. What about part C? We've got the definite integral from negative pi over 4 to positive pi over 4 of secant squared of x. So we need an antiderivative for secant squared. Now this is one that can be tricky, especially if you don't have your trig derivatives memorized. And by that I mean, do you remember what the derivative of functions like secant or tan of x are? And if you don't, this one's going to be hard. So I'll just remind you. Remember that the derivative of tan of x is actually secant squared of x. Now, if you didn't remember that, you can certainly write tan of x is equal to sine of x over cosine of x, and then use the quotient rule to differentiate. And then you, after some simplification, you'll eventually get secant squared of x. However, if you do that, that's not going to help you in this situation, because as if you would just randomly think to check that. Unless you remember that the derivative of tan is secant squared of x, tan of x is not even going to be on your radar for this. So it's really useful to have those trig derivatives memorized. But an antiderivative for secant squared of x is tan of x. And that ends up being important here. So tan of x is our antiderivative, and we're going to plug in our bounds. So negative pi over 4 was the lower bound, and pi over 4 was the upper bound. So go ahead and plug them in. You get tan of pi over 4 minus tan of negative pi over 4. And again, you have to play around here and actually work out the trig, but tan of pi over 4 is actually equal to 1, and tan of negative pi over 4 is equal to negative 1. So if you do the arithmetic, you just get 1 minus negative 1, which is positive 2. So that's what you end up getting for that one. I'm going to slide this up a bit. So part D now is our last one. We want the definite integral from 0 to 4 of the square root of x plus x. This one actually works out a little bit messy, but we can still do it without too much difficulties. So it helps to actually write this as the definite integral from 0 to 4 of x to the half plus x to the 1. Just to remind yourself that you're dealing with powers of x, because that way, when you go to take the antiderivative, you can use the power rule. So you're going to get x to the 3 halves divided by 3 halves for an antiderivative of x to the 1 half. That's using the power rule. Then if I do the power rule on x to the 1, I'm going to get x to the 2 over 2. So that is my antiderivative, and the endpoints are still 0 and 4, so I'll write those down. Now I'm actually going to even take a, oops, I better slide this up. I'm actually going to take a step just to clean this up because I hate dividing by fractions. So I want to write this as 2x to the 3 halves over 3 plus x squared over 2, and this is all from 0 to 4. Okay, so now I can plug these in. So I'm going to plug in x equals 4, so I'll have 2 times 4 to the 3 halves over 3 plus 4 squared over 2. That's what I get if I plug in 4. And if I plug in 0, let's just write it down. It's good practice to write it down, even though a lot of this is going to disappear. Right, if I plug in 0, that's what I get. And you can see, let's make that observation, just save yourself the trouble. All that's going to be equal to 0, because you get 0 squared, and you get 0 to the 3. 0 to the power of anything is 0, so both of those fractions are just going to end up being 0. So we have to worry about this now. Let's look at that 4 to the 3 halves. We got plenty of space over here. Let's work out what 4 to the 3 halves is. Remember, 4 to the 3 halves, that's just the square root of 4 cubed. And 4 cubed, you can work that out. That's 16 times 4, which is 64, and that's a perfect square. So it ends up working out to being 8. So that means this is actually 8 right here. So you have 2 times 8, which is 16 over 3. And then what do we have over here? 4 squared over 2, which is 16 over 2, which is 8. Did I do? Oh my goodness. Okay, I see what I did here. Okay, I wrote down the square root of x plus x. You might have already noticed this if you're watching, but the original example said the square root of x plus x squared. So to be honest, I'm just going to scribble this out and leave it as the square root of x plus x, because that's the example I've done here. I know that's cheating, but you've got the other ones worked out in the notes. You can check that one out. The only thing that changes is that this would be an x squared. This would be x cubed over 3. So that would change this and it would change this, but I don't want to go back and change all the stuff I've done, and I don't want to spend your time doing the example again. So just, I'm going to cheat here, and I'm going to change the example to the square root of x plus x, and that's the example that we did. So this is slightly different than the one that's in the notes, and the one I had intended to do. But in any event, that's what you have. So this, let's still simplify this. So I've got 16 over 3 plus 8. That would be 16 over 3 plus 24 over 3, which works out to being 40 thirds. So that's the answer if I change it to the square root of x plus x.